AP Statistics. This is unit number 2 over bivariate data. This is the second discussion topic that we went over in class. This was done on Friday after our first exam. So, least squares regression. We covered the formulas for finding the coefficients in the least squares regression line model, A and B. And this is not your traditional formula for B, but this one's the one that's most commonly used if you have these statistics given to you in the form of a statistical output based off of a computer program that will do that for you. We did most of the stuff in class for both my class periods, but I did not get to number 3 in either one of those. Maybe I got as far as reading some of the stuff here, but mostly I gave up and said, no, this is something I'll just go ahead and record separate. So that's exactly what I'm doing here. Number 3. I'll go ahead and read this out. It states, astringency is a characteristic of a wine that makes the wine drinker's mouth feel dry and puckery. So this was an actual paper, the paper analysis of tannins in red wine using multiple methods, correlation with perceived astringency, American Journal of Enology and Viticulture, 2006. This was an actual study, describes a study of the relationship between astringency and the concentration of tannins, chemical compounds found in the bark and fruit of some plants in the wine. The results of a statistical analysis is given below. On X, the tannin concentration, and Y, the perceived astringency. So I might want to underline those. That's going to tell me which one's X, which one's Y. So X would be the tannin concentration. Y is the perceived astringency. So that's like a self-reported value. Determined by a panel of tasters. So that's what the tasters perceive to be the level of astringency. So for 32 red wines was provided by the authors of that paper. So here we have what's called a Minitab Output. So the name of the computer program that's being used here. Very, very common. This is one I'd love to use in our classroom and practice some statistical programming skills. But that's not one that's free. And if I try to purchase that, it's a lot of money. That's not something the district would fork out. Because the calculators, for the most part, the calculators that we normally issue out are much better, much cheaper than just using Minitab. And Minitab is extremely, extremely powerful, way more powerful and overkill for the purposes in our class. But I wish we could use software like that, and that'd be pretty awesome. Maybe the only thing I've come across that's like that, that's cheaper, would maybe be R. And there's one more, but no. Calculators will be perfectly fine for this class, and which is the reason why I've never gone out of my, have made any significant effort to gain any licenses for that type of software. But either way, Minitab is one that's extremely common. You see them all the time in statistical textbooks, and the AP exam makes use of it as well. So the people who write the AP exam will make use of it and give out reports that look like this. You're supposed to know how to read those reports. So it's a very, very simple one. This one's a Minitab linear regression analysis. So linear regression output. So it's important that we understand the pieces of this and what each of these numbers represent. So really, you need to know that first line very, very well and the very, very first column of information. The rest of this we won't use until the second half of the course, towards the end of the course actually, the very, very last 6 weeks before we take our exam. So really the stuff that's important would be that beginning line, and it's going to give us the equation, the model equation, it's a linear equation, perceived astringency, equals to negative 1.59. There's no x on it, so we understand that that's A, plus 2.59 tannin concentration. So that's a multiplication thing going on there. 2.59 times tannin concentration. If you remember, tannin concentration is the x variable. This is B then, A plus BX is the format that they're giving that. So perceived astringency is your y coordinate. So y is equal to A plus BX is the equation of a linear regression model. So what they're going to do is they're going to still elaborate on that in the lines after that. So here we have our predictor. So we have two predictor values, the constant and the tannin concentration. These are two predictor parameters that are the result of the statistical output, the statistical computation that this linear regression output is meant to give. So the constant value, that is A. Tannin concentration, we understand that is the x variable. What they're actually giving is the coefficient for the x variable. So they line up. Constant is A, and that matches this A. Tannin concentration coefficient matches the B value that's up there. So under coefficient, constant is obviously A. Tannin concentration, whatever the x variable is, that's going to be B. And the rest of it, we kind of don't care what that's all about. So standard error of our coefficients, those refer to statistical inference procedures that we haven't gone over just yet. And these are the test statistic and p-values for those associated coefficients, standard error coefficient values. So these we'll understand how to use them later on. We won't need them for this unit though. So all we need here is this column right here. That's most important. So that's going to give us A and B. So if you know how to read that portion, that's basically all we need to know. You don't have to worry about it. So they're giving me A and B. Then they're asking here, calculate and interpret the correlation coefficient for this data. They want the correlation coefficient for this data. Actually, they didn't give me the data. They just gave me the numerical summarization of the data. All right, so if the sample standard deviation values for tannin concentration and perceived astringency are given here. So they're giving me that information for a reason. And we're going to try to find out that reason. So calculate and interpret the correlation coefficient. So correlation coefficient symbol is R. What they want is R. That's the goal of this particular problem. So then I have to figure out, why would they give me these standard deviations for tannin concentration, which is X, by the way. So if that's standard deviation, they gave me SX, and perceived astringency, so that's the Y variable value. So that's a standard deviation for Y. And those are the values given here. That is, let's see, and it says respectively. So tannin concentration is X, SX, SY for the second one. So I can still label these as X and Y. And they want the correlation coefficient. Is there a formula that relates R and those two standard deviation formulas? And the answer is yes. That's given up here. B is equal to, which B is the slope of the linear regression equation. B is equal to R times that ratio SY to SX. Let me write that down. B is equal to R SY over SX. So that's given there. So what I'd like to do then, that's just a simple linear equation that I could just, or it's a simple rational equation. We can consider it linear in R. And if I consider those other quantities B, SY, SX as constants, because they are constants, then this is a linear equation in R. And all I got to do is isolate the R variable. You would do that by multiplying by SY over, or SX over SY. So you would multiply SX over SY, as long as these are non-zero quantities, these will cancel. And again, it was SX over SY. So then you get R equals B times SX over SY. And I think I have all three of those values that I can use to plug in for R, B, SX, and SY. They told me that B, according to the information up here, is 2.5946 times, and they also gave me here, SX is 2.159, SY is 6.409. And that's basically all I need to calculate the value R. Later on we have to interpret it. So I have a calculator on the side. I won't show it on the screen because I have a physical calculator in my hand. 2.5946 times 2.159 divided by 6.409. Double check I did that correctly, and I'm getting 0.874. And I'm getting another 0.4, but that'll round to just 40. So 0.8740 doesn't round up to a 0.8741, so it stays that way. Now we need to remember R is just a unitless quantity, so that's given up here somewhere. No, I didn't give it up here somewhere. Okay, so that's something I'm going to have to address later. I didn't give information on R. Oh, I did. The information I gave on R was in a previous lesson, the first one. So I can go back to the notes for the first one. So correlation was covered in the very, very first handout. So if we're having issues remembering that stuff, it's all here. So the formula for calculating R by hand, which you won't be required to do that by hand, is here. So if you actually take a look at that expression really quickly, one thing you want to note about R is that it's unitless. 1 over n minus 1, if we do a dimensional analysis on here, 1 over n minus 1. N is just the size of a data set, so that's just a frequency, no units. This is just a summation symbol, so it's a summation of a bunch of these ratios. So I have to inspect those ratios. And you'll find out that those ratios are unitless. X is in X units. X bar is also in X units. SX is also in X units if you remember from Unit 1. Standard deviation is in the same units as the mean and as the data. So the actual X data. So this is unitless because you have units on X on top divided by units for X on the bottom. Units over units will cancel, or X units over X units will cancel. Same idea here for this expression. Y units minus Y units is Y units on top, divided by Y units on the bottom. Those Y units cancel each other out. This ratio is unitless. So since that ratio is unitless, the sum is also unitless since you're adding a bunch of unitless quantities together. Multiplied with this unitless quantity, R is completely unitless. So R has no units. And that should have been stated over here too. Yeah. So the correlation coefficient, so you always want to look back at your notes, especially before an exam. These things that I have here written in blue boxes are extremely important. Those are highlighted there so that way that's important information you can go back to whenever it is that you're studying or spending time preparing for an exam or later on AP review for the AP exam. 3 very important things that we need to know about the correlation coefficient. It's unit free, has no units. All right, so also as a quick corollary or quick consequence, R will stay the same after changing units of either X or Y. So if you change X, let's say for example was a distance value in meters, you change that to feet. R is still going to remain the exact same value because it's unitless. Units cancel out anyway. So that multiplier, the conversion factors, will just cancel out within the formula for R. Same for Y. If Y was in seconds, time, let's say seconds versus minutes or hours, it'll still remain the same because those units will get canceled out within the formula for R. So changing units has no effect on R. The size of R will give us the strength. The sign on R will give us the direction. And we do expect a value of R between -1 and +1, or after I take the absolute value, between 0 and 1. And the sign really just tells us what the direction of the relationship is. So going back to these notes, this is just R is equal to 0.874, which is a ratio. It's nothing but a unit-free quantity. All right, so how do I interpret it then? What is the interpretation of the correlation coefficient? Well, that was this second and third portion here that I just breezed over really quickly. So R will give us the strength of the relationship, and strength meaning like how close to a linear relationship that that data is going to be clumped together. The direction, whether it's positive or negative. As X is increasing, what's the Y coordinate doing overall? So it gives us those 2 bits of information. So going back to this particular problem, wrong one, here we go. This one's greater than 0, so this is positive. That's just a note that I'm writing on the side. Also, because it's greater than 0.5, it's strong. So that's a strong positive relationship. Assuming that there's a linear relationship, R tells us that there is a strong and positive correlation between perceived astringency and the tannin concentration, if I remember the variables correctly. So those I'm not going to record there. That's not part of my interpretation. You want to write it as a complete sentence. So we'll go ahead and say there is a strong and positive. We don't know if it's linear. R doesn't tell us if it's linear or not. If you remember from the third handout, we have to go by a residual plot. And if there's a pattern in the residual plot, then I can say it's not linear. If there's no pattern in the residual plot, then we say it is linear. So I have to go by the residuals, or I'd at least have to have a scatter plot to tell if it's linear or not. So R only tells me the strength and the direction, not if it's linear. So there is a strong and positive correlation between tannin concentration, and what's the spelling on that? 2 N's, 3 total N's really. Tannin concentration and perceived astringency. That's bitterness. It's a type of bitterness. Astringency. That's like a bad type of bitter. So there is a strong and positive correlation between tannin concentration and perceived astringency. That's what R tells us, and that's because 1, R is positive, not negative in this case, and 2, because R is a value that's really close to 1. Right, so we know that R is supposed to be between, or the absolute value of R is supposed to be between 0 to 1. The closer to 1 the value is, the stronger the relationship is. The closer to 0 that number is, the weaker the correlation is. So that's just a side note. That's just a fact. You're supposed to get 0 to 1, a value that's somewhere between 0 and 1 for the absolute value of R. That's disregarding the sign, that is. And that's going to be it for this particular handout.